So Tom Hartman will continue talking about quantum field theory and thermal physics and black holes with talk about chaos.
Okay, so part 3, I want to talk about scrambling, quantum chaos, and the connection to black holes. So I'm going to start by briefly trying to define the word scrambling, although it's a word that's hard to define. The idea is that you perturb a thermal state it could be just some bath of finite temperature stuff, or it could be a black hole. And we're going to perturb it, for example, by throwing in some bit. Okay, so there's a bit. You could think of this as acting with an operator or throwing in a bit. We're going to throw a bit into our thermal state or into our black hole. Actually, it doesn't have to be thermal. It could be, as long as it acts thermal, so it could be a high energy pure state, which acts locally like a thermal state. And we say that it is scrambled basically when this bit has been completely absorbed into the bath. What do I mean by absorbed? Well, we're going to discuss that, but think of it as there's some qubit worth of quantum information here, and when that quantum information is thoroughly spread amongst all of the degrees of freedom of your system, that's when we say that it's scrambled. So scrambled when this bit of quantum information is thoroughly mixed in. So the idea that this would be an interesting thing to look at for black holes goes back a long ways. And I'm just going to briefly tell you the history there. So why might you care about this for black holes? The basic idea is to consider a thought experiment where one person, usually called Alice, jumps into a black hole. And we want to ask what happens to Alice's quantum information. So maybe Alice is carrying this bit, and she's jumped into the black hole. And the question is sort of how that bit gets retrieved or recovered through the Hawking radiation. So she jumps into a black hole with this bit. The black hole radiates. It evaporates. And eventually, if the evaporation is unitary, then this bit has to be released in the Hawking radiation in some sense. But this leads to a potential paradox, because if Bob waits outside, collects the Hawking radiation, and decodes that bit from the Hawking radiation, then you can get into a problem with quantum mechanics. Because Alice still has the bit is here, bit, and now Bob has collected the bit on the outside and has jumped into the black hole. So we seem to have two copies of the bit, but we have a problem then with the no cloning theorem that says that we shouldn't be able to copy a bit in quantum mechanics. So this seems to be an issue, and it really becomes an issue with this work of Hayden and Preskill, who showed basically how easy it is, well, easy relatively speaking, to extract a bit of information that's fallen into a black hole. All you have to do is the following. So Bob watches this black hole for a very long time, watches it evaporate, and collects all the Hawking radiation, and waits long enough that Bob has collected at least half of the information in the original black hole. Okay, so this is past what was called the page time, when it's half evaporated, and Bob has collected that information completely coherently, say in a quantum computer or something. Then what Hayden and Preskill showed is that if you throw a bit, so now Alice throws in a bit, then as soon as that bit gets mixed up into the black hole, it's released effectively in the next Hawking quantum. Okay, so the time it takes, so if Bob has already collected all of this Hawking radiation, then the time it takes Bob to retrieve the bit is just as long as it takes for the bit to be fully scrambled. So the bit falls in, it gets mixed up into the quantum state of the stuff making up the black hole, and then can be extracted immediately as soon as one more Hawking quantum has been emitted. What this means for the no cloning theorem is that, from the no cloning theorem, this means that it better not scramble too fast. It better not get mixed up into the black hole too fast, because if it does, then it'll just immediately, like say you drop a bit into a black hole and it immediately scrambles. Well, then it's immediately going to be released. Bob is going to have plenty of time to collect that bit, jump in, and have a meeting with Alice on the inside and reach this contradiction. So the no cloning theorem sets a lower bound on how fast scrambling can occur. And the bound that was derived this way is beta log n, or log s, where n, so n, or the n is essentially the entropy of the black hole. It's the number of states. Note that Ts, the scrambling time, is much greater than the thermalization time, which for a black hole would just be of order beta. Okay, so if you drop something when you drop something into a black hole, the black hole, classically speaking, so if you calculate some correlation functions or one-point functions, classically speaking, this black hole very fast returns to an equilibrium state. That's the thermalization time, and it happens of order the size of the black hole, or the inverse temperature. The scrambling time is a much longer time because it has this log n. N is huge, so that log n is making the scrambling time much later than the thermalization time. Okay, so the basic picture is you jump into a black hole, or you throw something into a thermal system. It very quickly thermalizes, but gradually that bit gets, but it takes a while for that bit to get fully mixed up. Yeah.
Is it clear that that bit is still there inside of the black hole, that Alice still kind of holds on to it?
Could you repeat the question?
Yeah, the question is it clear that Alice still has the bit? Well, I think if there was no scrambling, if scrambling was immediate, then I think it would be clear. If scrambling happened immediately, then Alice is just holding the bit. I mean, this is a perfectly reasonable semi-classical geometry. Alice is holding the bit. If scrambling happens immediately, Bob just has to wait a few minutes and jump in, and if this is a big black hole, there's nothing preventing him from comparing the bit with Alice.
You're assuming they don't crash into a firewall.
Yes, I'm assuming they don't crash into a firewall.
Is it clear that when stuff evaporates, that information just doesn't go outside somehow?
Well, this sort of gets into how if you wait a long time, then you're saved. If the scrambling takes long enough, then what basically happens is that Bob is jumping in way up here somewhere, and it's impossible for Alice to get the bit to Bob. So that's how having a long scrambling time saves you from violating the no-cloning theorem. So you're right, but it requires this large scrambling time.
I think it's worth pointing out that the work they have done, they say that it is not violating the non-cloning theorem. It's because they argue that it is a transplanting problem by investigating in detail how much time that Bob is jumping to the black hole and how it is possible to compare it with Alice.
Yes, I have not explained the details of how you resolve this by waiting the scrambling time, which is what you're talking about. But this is it's related to what you just said. I'm not going to really get into that. This is kind of all I want to say about scrambling. And what I really want to do is I wanted to use this to motivate just that this vague idea of things getting mixed up into a thermal system is an interesting thing to think about and is related to these black hole paradoxes. But also that scrambling and the scrambling of black holes, in the early work, the definitions of these things were sort of vague. And part of the big advance in the last few years in terms of thinking about this in terms of chaos has been another way of thinking about scrambling that gives you something very precise and very concrete that you can calculate and use to define the scrambling time. So that is what I'm going to talk about now and for the rest of this lecture. And this is work of various people over the last few years, especially Schenker, Stanford, Kitaev, and various other people. The idea is the following. We're going to act on the thermal state rho beta with a probe operator psi of x. I call it a probe operator because I don't want it to completely violently change the thermal state. I don't want it to radically change the temperature. I just want it to insert a little bit of energy, a little bit of stuff. And so if we insert an operator in some thermal system, it's going to do something to the quantum state. And it's going to do something to the quantum state in the future light cone of that insertion. But the question is sort of what the action of this operator does to the quantum state. There are various things you could mean by insert a probe operator into a thermal state. And actually, the details don't matter that much for this discussion of chaos. But for concreteness, and because it's very convenient in quantum field theory, the exact experiment that we're going to consider is to perturb the thermal field double by the insertion of a local operator. So beta is my thermal field double state that we've discussed, and I'm going to define a perturbed thermal field double by inserting an operator psi. So this is psi at imaginary time beta over 4 and some position x, which I will mostly drop and not keep track of, acting on the thermal field double. In terms of a path integral, remember that the thermal field double was this path integral on the strip of size beta over 2 with cuts at the top and bottom. So we're talking now about a perturbed state where we insert some local operator psi, which is not too heavy, just right in the middle of the strip. If I call so the thermal field double lives in this h left times h right, which correspond to the two cuts on the strip. And remember that the state beta gives you a reduced density matrix on the right, which is just the thermal state. Well, the state psi beta will give you a reduced density matrix on the right, which is a slightly perturbed thermal state. The question then that we want to ask is how fast does this perturbed state psi beta become completely different from the unperturbed thermal field double state beta. What do we mean by completely different? That's the next thing we need to do, is define what we mean by completely different. And to do this, let's remember what the thermal field double looks like. It looks like a highly entangled state between the left and the right, where the entanglement is local in space. So this bit on the right, or this position on the right, is highly entangled and highly correlated with this position on the left. There's some spreading out of those correlations of size that spreads out over a distance beta. So in the state beta, we have these nice correlations between left and right. And that means that what we're going to do is we're going to diagnose whether it's completely different by measuring these left-right correlations. So we diagnose different by measuring the left-right correlations. Now, there's still various ways that we might try to measure the correlations between the local correlations between right and left. There are information theoretic ways to do that. You can calculate what's called the mutual information of this region with that region, for example. I'm not going to go into that. That's an entanglement entropy type measure that measures correlations in that quantum state. But we can also do it a little bit in a sort of a more pedestrian way, just by measuring correlation functions. And that's what we're going to do. So that's what we're going to discuss. We're going to measure an operator on the left at time t. We're going to measure the correlations of an operator on the left and right at time t. So this is what we're going to use. If we work in the unperturbed state, just the ordinary thermal state, well, the ordinary thermal state is time independent. So this is just time independent. And we're going to normalize our operators, so this is just 1. Okay, so in the ordinary thermal field double, they just stay, the left and right just stay perfectly correlated forever, and that's measured by this 1. But if we do this in the perturbed state, so let's define g of t to be psi beta O left of t, O right of t, psi beta, in terms of a path integral, let's see if I can draw this as a path integral. Okay, so I'm not going to try to draw the space direction. I'm just going to draw the time direction. Okay, so first we prepare the perturbed thermal field double state. Okay, so how do we prepare this thermal field double? We do Euclidean evolution of distance beta over 2 with the psi operator inserted in the middle. So that's this state on the right. Then we're going to insert the operator O of t in the right. Okay, so at this point I have to continue into Lorentzian. So this is now Lorentzian time. Insert the operator O right of t. And I'm going to insert the operator O left of t in the same way. Okay, so this one goes in time, and we insert the operator O left of t. And then we have to get our bra. So we go back and finish the path integral by closing the circle. With another psi insertion in Euclidean time. Okay, so there's this weird folded path integral. We're doing the path integral on remember there's space here that's been suppressed. So there's path integral on the cylinder, and then we've inserted operators on the right and left and moved them off into Lorentzian time. Yeah? It's neither. It's neither. I mean, so the question was whether psi is on the left or on the right. And the answer is that you should think of psi as being defined by where we put it in the path integral. I'm going to write now an expression in terms of the trace, which might clarify this. Any questions about this picture first? Does this picture make sense? I could stop here and just explain this picture forever. So it gets super confusing. We're happy with the picture? Okay. In terms of a trace, anything in a thermal state can also be written as a trace. So the trace that we're doing here, well, we can read off the trace from this path integral. Okay, so the trace has, let's start by inserting O of t. And we'll write that as our first thing in the trace. So we insert O of t, then we evolve by beta over 4. We insert psi, we evolve by beta over 4. We insert O of t again, evolve by beta over 4, insert psi, evolve by beta over 4. So as a trace, if I start from right and go to the left, first we insert O of t, then we evolve by e to the minus beta h over 4, then we insert psi, then we evolve again by e to the minus beta h over 4, then we insert O of t again. I'm going to run out of space. This is too bad. Psi. Oh, no. We did it. OK. Beta h over 4. Notice now that I've dropped the labels left and right on O of t. This is now not referring to the thermal field double. This is just referring to ordinary quantum mechanics in a mixed state. And O is just an operator in that single copy of the Hilbert space for the ordinary quantum mechanics in the mixed state. Is there a question?
Is this actually a picture on the tau plane? As a concept?
No. No, not really.
What's the question?
The question is whether I should really think of this as the complex tau plane. No. No. Tau circle. It's not the complex plane. This is just a schematic representation of the path integral that we're doing.
This is just like a square on the top plane.
In the tau plane, that's right. If we literally did this in the tau plane, then I guess we should just go we should go beta over 4, then go in real time, then go beta over 4, then go beta over 4. It would be like this: psi, O, psi, O, and then we identify the ends. So what I've done here is I've just wrapped up that picture to make it look more periodic. Yes? Oh, did I miss one?
Yeah, between
Oh, sorry.
psi and O.
Yeah, okay, that's because I was running out of room. Yeah. Altogether they have to add up to e to the minus beta h, because we're working at temperature e to the minus beta h. Thank you. Other questions? Yeah.
Why do you have to go back to the original plane where you inserted, why do you evolve back?
Why do you evolve back? Because O of t is e to the minus iht, O times e to the iht. So that's what O of t means as an operator. It involves going forward, inserting the operator, and then going back in terms of path integrals. Other questions? This thing is called the OTOC. For out, maybe it should be the UTOC, the out of time order correlator. Nobody puts the little O. Okay, so this is the out of time order correlation function because of this crazy looking picture where we start in the past, we insert an operator, we go forward, we go back, we go forward, we go back. Okay, so this is the OTOC. And remember the physics of scrambling that we're interested in is, so we're asking when this OTOC becomes small. So if this correlator is large, then it has not scrambled yet. But if g of t starts going to 0, then we see that it's starting to scramble because the correlations between the left and right sides of the thermal field double are getting messed up by the insertion of this perturbing operator. So this correlation function can be calculated using a black hole. The black hole picture is very similar to these pictures that we were drawing over there. Well, let me first draw literally what's over there, but now in black hole language. Okay, so we have this operator O inserted here, and we have another operator O inserted here, and we've also gone into Euclidean time. So if at time 0 I patch on this Euclidean circle, then we have the operator psi inserted halfway around the Euclidean circle. So this is the correlation function we're calculating on the black hole. One second, because I think I know what you're going to ask. This O looks upside down No. Okay, I'll come back to you. This O looks upside down from what I drew over there, but that's because T runs forward on the right side of the Penrose diagram, and T runs backward on the left side of the Penrose diagram. So even though they both went forward in T, one of them goes backward on the Penrose diagram. Is there a question? This is just a useful, very symmetrical way to think about things. Sorry, the question was why we stuck psi halfway around. For example, we could have, if we had just said, let's study some correlation functions in a black hole, then we might have tried inserting things in Minkowski. Like we could just put O here and psi here and O here and psi here, for example. This correlation function is very closely related to this one just by shifting in imaginary time. I've started with that one just for convenience, really. I mean, if you want to, I guess thinking about it as the reason I like this one is because we can think about it as a quantum state. When we have the thermal field double and we insert an operator offset Euclidean time like this, we can think of this psi beta as a normalizable quantum state. If I had inserted psi at the cut, that would correspond to the picture there with the things actually inserted in real time. That's fine as an experiment, but it doesn't quite have this interpretation of being a quantum state that you're evolving, and it's slightly less symmetrical. You can work with the other one. Actually, the other one will come into the argument when we talk about the chaos bound, and the behavior of the correlation function really doesn't care very much whether we calculate this one or this one. They basically have the same correlation function up to some shifting t to t plus I beta over 4. So we can now calculate this 4-point function holographically. In fact, this is easier to do in this picture because in this picture, well, it's just hard to think about spacetimes with insertions in complex time. In this picture, the calculation of this correlation function is just a 4-point function where you're scattering things. Okay, so if we calculate a 4-point function like this, if t is large, so t is the separation between these. So if t is large, then there's going to be a large center of mass energy. So there's some scattering happening between O and psi. And if t is large, there's going to be a large center of mass energy in that scattering process. You can calculate this in this limit. You can calculate this in a very convenient way, which is using shock waves. So I'm not going to really describe the calculation, but I'll just draw a picture. What you do is you think of these psis, the psi insertions, as creating a shock that's basically on the horizon. I should have moved it lower down, then it would be more clear it was on the horizon. So we create a shock wave. And then we calculate the 2-point function of O in that shock wave. Okay, so the 2-point function of O in this perturbed state is just the 2-point function of the shock wave. That you can calculate, well, the easiest way to calculate it is to assume that O is massive and just calculate a geodesic length in this shock wave background. Okay, so then you have O moving on a geodesic in the shock wave background, and G of t is e to the minus mass times the length of the geodesic. Yeah.
Do you necessarily need the black hole for the shock wave?
No. So the question is whether you need the black hole here for the shock wave. No, you can have shock waves in flat space-time. And in fact, most of what I'm saying carries over to flat space-time in the sense of Rindler space. So you can think of scattering in flat space-time as being finite temperature by using Rindler coordinates. And then a lot of what I'm saying carries over to flat space, to just ordinary correlations in vacuum using that map. Okay, so the calculation that I just described but won't do gives the following for G. 1 minus 1 over n squared e to the minus lambda delta x over VB e to the lambda t. So let me describe what all of these are. First, lambda. So lambda, from the black hole calculation, is 2 pi over beta. And what is lambda telling us? Well, the correlator starts out 1. At time 0, the correlator is 1. And then as we evolve in time, it starts to go away from 1. Okay, so the n squared here is huge. So what we're seeing is that it starts out 1, and then it starts to exponentially deviate from 1. So that exponential deviation is interpreted as quantum chaos. In a classically chaotic theory, when you have nearby classical trajectories that are slightly different, so if you slightly perturb your initial classical trajectory, then you will move apart. You'll move apart exponentially fast in time in phase space. That exponential deviation from your initial state is the Lyapunov behavior, and lambda is called the Lyapunov exponent. So the most important thing in this equation is this Lyapunov growth, e to the lambda t. The other things that are happening here, so n squared is the strength of the interaction. So we're working with a theory that's perturbative in ADS. So we're doing some scattering in ADS, and 1 over n squared is the strength of that scattering. So that's why there's that 1 over n squared out front. This factor appears if you separate O and psi in space. I haven't really kept track of the space dependence, but if they're separated in space, well, then you'd expect some additional suppression of this effect, and that's what this is. So this is called, well, VB is called the butterfly velocity, and it's the fact that it takes some time for chaos to spread in space. It spreads linearly because it's linear in t and x, t and delta x in the exponent here. So chaos spreads linearly at the velocity VB. That depends on what?
On what the probe psi actually is.
No. Let's see. Lambda and VB don't depend on the details of the probe. There's a numerical coefficient here which depends on the details of the probe, but that's the only thing in this equation is the number out front.
What is
I don't remember the formula, but it's something like the square root of some function of the space-time dimension. It's like a half or 2/3 or something in 4 dimensions. Some reasonable number. It's not 1 though. some reasonable number that's less than 1, unless you're in 2 dimensions. Okay, so the picture in real time of what we've described is that we've at time 0 we've perturbed the system by inserting the psi operator, and then we're asking what happens to the quantum state? When does it scramble? So what I want to draw is the spread of chaos in space-time. So let's start at the origin. Okay, just right on top of the psi operator. Then we can ignore this term, and we see that chaos starts. Well, this is scrambled when this whole thing becomes order 1. Now, if it's literally 1, we don't trust this calculation. So let's say it's scrambled when this whole thing is equal to 1 over 100, or 0.1 or something. Okay, so we're going to plot the region where g minus 1 is greater than 0.1. If we sit at the origin, then it takes the scrambling time, which is beta over 2 pi log n for this to become order 1. Right? The beta over 2 pi, that came from the Lyapunov exponent that sets this time scale, and the log n came from the fact that this was suppressed by 1 over n squared, so we need to compete with that suppression. So if we want this to be scrambled, that's the amount of time we have to wait. So if we sit right on top of this perturbation, we have to wait the scrambling time Ts, and then we'll see that it's scrambled after that. Yeah.
Should it be each the 2 lambda t rather than each the lambda t?
Otherwise, the scrambling time would be twice as large, and the scrambling time isn't twice as large.
Well,
Actually, sorry, it should be log s rather than log n, shouldn't it?
Yeah, I'm not really keeping track of that factor. I don't think the code. It's definitely e to the lambda t. As far as that factor of 2, yeah, maybe I should call it log s, but I'm not really going to worry about the prefactor. Is that prefactor meaningful? I'm not. Yeah, I guess it's meaningful once we define it carefully, but yeah. Okay. Yeah, let me not worry about the prefactor. Okay. Now what about the spread? Okay, so it's also spreading at the butterfly velocity, which is not 1. So if I draw the light cone coming out like this, then the butterfly velocity is something less than that. So let's draw it like this. Okay, so this is the scrambled region. The way to think about this is that we're in a system with a large number of degrees of freedom at each site. Okay, so there's a huge number of degrees of freedom sitting right here at the origin, and it takes a long time for this bit to get mixed up into that large number of degrees of freedom, and it takes some time for it to spread in space. So we're seeing those two effects. Any questions at this point? So that was I was describing this as a black hole calculation, but this is actually very general behavior of out-of-time order correlation functions. So more generally, there are a lot of systems where you have OTOCs of this form. That is, G looks like 1 minus epsilon e to the lambda t. you can see this in spin chains. And you can potentially, well, you can see it in physical systems like cold atoms, which are essentially spin chains. So this goes way beyond just black holes, but it was sort of motivated by these kinds of experiments and thinking about black hole scrambling. So this is something that people have gotten excited about very generally beyond just quantum field theory. Yeah. Yes. Here where? Oh yeah. Yeah. Psi is slightly away from the board, but but it's only spread over size beta, right? Because it was only a distance of beta over 4 from the board. So there's a little blob here of size beta. But on the scale of this diagram, that's a dot. Yeah. Other questions? Yeah. You mean how do they measure them in real physical systems? I don't really know. There are a lot of papers about this. I don't know how they measure it. Okay, so this is a very general phenomena, and now we get to the chaos bound. Of Maldacena, Schenker, and Stanford, which says that in almost any quantum system, lambda is less than or equal to 2 pi over beta. So the black hole is maximally chaotic. So this is not just a fact about quantum field theory, but we're going to sort of work in the context of quantum field theory to prove it. I should mention this epsilon, to really make sense of this epsilon here needs to be small. And in a general quantum system, you don't have 1 over n squared. Okay, so there's no, in the more general case, there's no 1 over n squared to suppress this Lyapunov behavior. But there generally is a suppression coming from separation in space. Okay, so even without the 1 over n squared, you can still use these OTOCs to measure chaos, and you can still measure the spread in space. You just have to use this. This factor is essentially defining the suppression for you.
There's a question in the back.
Yes?
What are the exceptions to this? We're almost.
The question is, what are the exceptions? Well, there are exceptions like in free theory, and we'll kind of see that when we're going to do the proof now, and we'll kind of see where that comes in. There are theories that don't really have this behavior. So free theories don't really scramble in the same way that interacting theories do. So the exceptions mostly look like that. The question is, should we worry about this becoming negative when we go way past the scrambling time? And the answer is no. Let me draw a plot for that. So as a function of t, we're measuring this g of t, and it starts out around 1. And here it is, 1 for a long time. And then it starts to deviate from 1 exponentially at around the scrambling time. So this is the onset of chaos. And throughout this discussion, we're only talking about this piece of the curve. What we expect to happen at later times is for this to go to 0. But at that point, this approximation breaks down, and we aren't going to talk about it. There's things you can say about it, but we're really only talking about the very early times where where we can still work perturbatively in some sense because G is near 1, but we start to see this exponential deviation from 1. That's why I define the butterfly, the scrambling region, as like the correlator being deviating by 0.1 instead of by 1. Maybe 1 over 100, whatever you want for it to be well controlled.
This is a large n-bound.
The question is this a large n-bound? And the answer is no, actually. I don't know that I don't think this was clear in some of the original work on this, and I think it wasn't so clear in the original paper. It seemed that they were essentially, so it's essential for epsilon to be small. That's essential. And if you don't talk about the separation in space, then, so like if you just talk about, say you spread your operators uniformly over space, then this factor is not here, and then it only makes sense to talk about this at large n. So you really need this to be small. But if it was really just a large n-bound, then all the people studying spin chains and everything wouldn't be so excited about it. The reason they're excited about it is because this suppression in space factor actually gives you essentially the same result for small n systems, as long as you work with localized operators. Yeah?
So it could also be like a semi-classical chaotic system and epsilon be H1.
The comment is it could also just be weakly coupled, and this could be the weak coupling. Yeah, that's right. That's right.
I think that people say that there is no precise definition for the approximate exponent for the non-large n system.
Well, there's a question of whether you can really match to it. Sorry, I'm supposed to repeat it. The comment was, wait a minute, you can't really define the Lyapunov. And that's true. I mean, you can't really match. If this only happens for a little bit, then you don't have a precise way of assigning an exponential dependence to that. But you can see that it's not 1. Okay, so you can measure scrambling. You can see that it's not 1. You can still measure something like this and say when it's deviated from 1. But it's true the Lyapunov itself is not necessarily well defined. Yeah, thank you. Yeah.
Is the point that at large separation in a spin chain, say, the kind of functional form can be different from that delta x plus lambda t, but that the growth is still bounded? Is that kind of?
The question was whether in a spin chain this thing could look different, but that it would still be small. Is that the and?
Still some bound of how it grows.
Well, the bound is on this thing. The bound is on this growth. This is just sort of playing playing as the role as the factor of epsilon.
The question is whether the functional dependence in spin chain is really that.
I see. You're questioning whether there's meaning to the chaos bound really in that case. I'm not really sure what the story is there. I think that's sort of been evolving, and I think I'm not sure really what the answer is in the spin chain case. I'm going to prove this in the large n case, in the QFT case. So there I'm happy with it because we're going to prove it. For these more general cases, I'm not sure what the story is there. Okay. I think what I'll do is I'll leave up that G and start working on this board. Okay, so the proof of chaos bound So what this really relies on is understanding carefully the analytic structure of this correlation function g of t, which I'm now calling g of tau because I want to analytically continue on the complex time plane. So what does this analytic structure look like? On the tau plane, so here's imaginary time running to the right. I'm going to draw, let's see. Okay, so I'm going to put beta over 2 here and minus beta over 2 here. So this is periodic in, sorry. It's not exactly periodic in beta, so let me explain why. So there's this parameter t, but it's controlling 2 of the operators. Okay, so on the thermal circle, let me draw this thermal circle again. So on the thermal circle, we have an operator O of t, then we have psi, then we have O of t, and then we have psi. So if we start shifting t in the imaginary direction, it's actually periodic in beta over 2. Right? Because when we move t, we're moving both of the O's. Okay, so this function is going to be periodic in beta over 2. And it's going to have branch cuts when O hits psi. Okay, so we branch cuts at beta over 4 and periodicity of period beta over 2. So let me draw that on here. So there's a branch cut at beta over 4. Above and below the real axis. So the reason this is separated, the reason this is up is because they're separated in x. Okay, so the branch cut is really when t hits the light cone of psi. Okay, so this is the psi insertion, and it's separated up by a distance delta x. It's periodic in beta over 2, so if I put minus beta over 4 over here, then we see those again. And it just keeps repeating like this on the tau plane. But we're just going to focus on this strip here. Of size beta over 2. Okay, let me pause here because I know that pictures are kind of hard to follow quickly. Did that make sense? Any questions? Should I walk through it again, or we're happy? Yeah.
Maybe this is a dumb question, but am I supposed to imagine that like size inserted at x equals 0? Or?
Well, I didn't really assign it an x, but they're separated by delta x. So put psi at x equals 0 and O at delta x.
Both those at delta x?
Yes. Other questions? So this is the analytic structure of this correlator. And I don't know if do I have color? I do have colors. Oh, good. You're all rescued. Okay. Okay, so what we're going to do is we're going to focus on this thing here, on this region here, which I'll call S for strip. And to prove the chaos bound, we're going to look at the analytic properties of the correlation function on region S. First of all, how do we connect to the actual chaos bound? Well, the chaos bound was telling us about the onset of chaos at the scrambling time. Okay, so we're going to assume that here on the bottom of the strip, G is approximately 1 minus epsilon e to the lambda t. Our goal is the following. We want to say if G behaves this way at early times, we want to constrain lambda. That's the logic. So we're going to assume that here this bottom of the strip here is going to be placed at the scrambling time, or even well before the scrambling time. And so we assume that the correlator behaves like this here. On the edges of the strip, we'll prove that G is bounded by 1. We'll do that using unitarity. We also have to worry about the asymptotics at late times. I'm not really going to talk about this, but you can show that it's analytic. So we need it to be analytic going up towards infinity, and it is. Okay. So I claim that already, if you buy what I just wrote here, that it's analytic on the strip and bounded by 1 on the right and left, and has this Lyapunov growth at early times, then you're done. That gives you the chaos bound. So at that point, this is up to an assumption that I'll input in a minute. This is just a math theorem. And the intuition for this is that analytic functions well, they're analytic. So the behavior in one direction is related to the behavior in the other direction. And the problem is that if we make lambda too large, suppose we make lambda huge, then this function is going to be rapidly oscillating across as we move across this line here, right? Because this is the imaginary time direction. So a big lambda is going to be rapid oscillations along the bottom of the strip. But rapid oscillations of an analytic function in one direction correspond to rapid growth of an analytic function in another direction. Okay, so if I try to make it oscillate too rapidly along here, then it's going to grow too rapidly along there and violate the boundedness along the edges. That's the logic for the proof. Is there a question? Well, actually, G does, in many cases, tend to 0, but for the proof, we just need it to be analytic. So the question was, why doesn't it go to 0?
Are there physical inputs in that assumption?
About it going to 0? Or
At least the boundedness property.
the question is whether there's physical inputs going into the behavior up here. And the answer is yes. In general, that's an assumption, but in examples, you can actually prove it. In some examples, you can actually prove it. Other questions? Okay, so we only have, how long do we have to prove the chaos bound?
11 minutes.
11 minutes. Okay, perfect. So we're going to prove the chaos bound in 11 minutes. What part do I want to do? Maybe I'll just very briefly sketch why G is bounded by 1, and then I'll tell you how we get from here to the chaos bound. Okay, so this is not going to be totally satisfying. I just want to write the equation up, and then you can ask me about it afterward for why it's bounded by 1. But this really is sort of the crucial, it's really sort of the crucial input to the result, is this boundedness, and it comes from unitarity, so I want to say where it comes from. So if we're talking about G on the so we're talking now about the edges of the strip. And the function g along those edges is g of t plus I beta over 4 because, so we're talking about the function along here. So this is the edge. So this function t of I beta, or sorry, g of t plus I beta over 4 is the one where on this picture we've rotated the O's to be right next to the psi's. Right? So we've rotated this by I beta over 4, and they're just sitting right next to the psi's. So as a trace, the O's and psi's are just next to each other. This is e to the minus beta h over 2 O of t psi e to the minus beta h over 2 O of t psi. Now, we can argue that mod g is bounded by the other operator ordering. So I'm just going to switch. So this was the OTOC, O psi. And I'm going to bound this by the time-ordered one, or by the one where these are flipped. So this psi O of t e to the minus beta h over 2 O of t psi. Where did this come from? So where did we get this bound? This bound came from a Cauchy-Schwarz inequality, which says that the inner product, the absolute value of the inner product of two vectors like that is bounded by the trace of x dagger x. I'm not going to take the time to super carefully write this out, but you can kind of see how that would work, right? Because the x is basically is basically psi o. So when you have an inner product like this, you can use Cauchy-Schwarz to bound one operator ordering in terms of the other operator ordering. That's the first half of the input here. Now, this thing that this other ordering that we're using, so this is just beta psi OO. And the other physics input that we're going to use is to assume that this is just going to factorize. Beta psi beta beta OO beta. This is an assumption. This is not always true. In free theories, this is not true. In two-dimensional theories and Virasoro symmetry, I think this is not true. But it makes a lot of sense, because what are we doing here? We have a thermal bath, and we're inserting two operators down here, measuring their correlation, and two operators up here, and measuring their correlation. If we do this in a time-ordered way, this should just completely factorize. I mean, if just the fact that we inserted these operators at early times should be completely washed out by the fact that we're in a thermal state. By the time we get to late times, this two-point function couldn't care less that we've inserted these operators at early times. So this factorizes, and that gives us. We've normalized our operators, so this is 1. So that gives us this bound g less than or equal to 1 on the edges. Question? Yeah.
So corrections are recorded T over beta to that approximation?
To this approximation? I believe they're exponential. At late times, I believe the corrections to this are e to the minus t over beta. Yeah. Okay. Maybe I'm just going to skip the math part. So I only have 5 minutes, and I'm going to say a little bit more physics. The math part is, there's just a theorem that if you have functions that act like this, then they can't oscillate too rapidly along the strip. And you can convince yourself, it's not a complicated theorem. In the original paper, they used some fancy complex analysis theorems. But actually, if you're willing to make some plots and just stare at these pictures a little bit, you could very easily convince yourself that it's impossible for lambda to be too large. It violates the maximum modulus principle. What you do is you compare, you plot the function. You just take this function and you plot it along this strip. You plot its modulus. Now you don't know what it is along the edges, but it's less than 1, so that's all you need. Then you plot it again on a strip that goes to a slightly later time. So you just plot the function along the original strip, then you plot the modulus again along this strip, and you'll find that then the maximum modulus principle says that the maximum modulus has to decrease when we shrink the region, and you just make some plots. You can convince yourself that this is impossible to obey unless lambda is less than 2 pi over beta. So maximum modulus implies lambda, but implies, first of all, epsilon is positive, and secondly, lambda is less than or equal to 2 pi over beta. So I encourage you to make those plots. I mean, you literally just plot this function along the strip and try various values of lambda and see if you can get the maximum modulus principle to be obeyed or not, and you will fail if you make lambda too large. Okay, now I want to take 3 minutes to list some cool consequences of this. Well, one I mentioned in response to a question is that Rindler space is a finite temperature quantum field theory that obeys the assumptions of this theorem. And in fact, many of the things that were assumed in deriving the theorem you can prove in Rindler space, because we know a lot about the analytic structure of correlation functions in Minkowski. So Rindler space, using Rindler space, you can infer that the chaos bound constrains vacuum correlators in flat space in quantum field theory. Okay? In this case, so I'm sure you'll hear more about Rindler space from Tom Faulkner, but the analog of these thermal pictures and black hole pictures and everything that we've been drawing is just the splitting of Minkowski space into left and right Rindler wedges. And what you end up constraining are these correlation functions. You can constrain correlation functions like this, where you have 2 operators in each of the Rindler wedges, and you send these operators out to infinity so basically you do a large boost on these operators holding the separation fixed. So you just take this picture, and as you send it to infinite boost, that's the regime that's constrained by the chaos bound. The second cool consequence
These are correlated. The P is a contribution already in the free theory, right? Is that right or not?
So the question is whether these receive a contribution in the free theory. The disconnected contribution here is just the one. So there won't be any Lyapunov. Right. Yeah. So the second consequence I want to mention is an ADS. Okay, so let's go back to this black hole picture. So when they did these calculations of scattering through a shock wave, they used Einstein gravity originally. You can include stringy corrections and consider other things. But this answer that I wrote here with maximal chaos comes from Graviton Exchange. Okay, so what you're doing is you have this high energy shock wave and you're sending a probe through it. A graviton is going to be exchanged in that process. And this fact that lambda is equal to 2 pi over beta in gravity comes from the fact that the iconal phase for scattering with the exchange of a spin j particle goes as s to the j minus 1, with j equals 2 for the graviton. Okay, so it's the fact that you were exchanging a graviton in ADS that led to the saturation of the chaos bound. And more generally, this S becomes e to the 2 pi t over beta. So what that means immediately, it immediately tells you that you're going to violate the chaos bound if you try to exchange a particle of spin higher than 2. Okay, so if you try to exchange, say, just one spin 4 particle, then you'll violate the chaos bound, and therefore you can exclude finite towers of higher spin particles in anti-de Sitter. That bound seems to also carry over to flat space, although there the arguments, the understanding of the analytic structure of the S matrix is not as good as the understanding of the analytic structure of these position space correlation functions that I'm talking about. So a lot of the things carry over to ADS, but they sort of carry over as conjectures, whereas they're theorems in CFT. Holographically, that gives you theorems in ADS, and then they carry over as conjectures into flat space, because it's really the flat space scattering amplitude that's controlling this process. So you learn about the scattering in flat space. Of course, we know in reality there can be higher spin particles. We have them in QCD. We have them in string theory, but they come in infinite towers. And when they come in infinite towers, that can modify this behavior in a way that it does obey the chaos bound. So if you include the full tower of string theory, for example, then the Lyapunov exponent actually decreases. Whereas each individual spin seems to be trying to violate the chaos bound, but when you add them all together, of course, famously softens in string theory and obeys the chaos bound. Questions? Yeah.
So the iconal approximation might not see the whole picture. Iconal approximation only sees the part where the distance between the two shock waves are not zero. Impact parameter is not zero. So iconal approximation does not see the part which is sort of, say, the part in the scattering that comes from contact diagrams.
Yeah.
So the conclusion that if it is based only on iconal approximation and social conclusions, that does not say anything about the.
Yeah, so the comment is that this is the iconal scattering, which doesn't constrain contact diagrams. It seems so. This is what I'm describing here is like the original picture that corresponds to the original calculations that were done over there. It's believed that this implies a stronger bound just on the amplitude itself, on A. So in iconal scattering, this is some tree-level exchange, and it's believed that this bound carries over to the scattering amplitude A and essentially tells you that A can't be bigger than S squared. Yeah. That step is a little more complicated, I think, and I'm not sure, I didn't mention that one because I'm not exactly sure to what extent that's a theorem or a conjecture or exactly all the properties that go into that. This one is 100% solid. This is what it literally, if you just do this experiment, you literally get this bound. Other questions? All right, stop there.
We'll come back at 2 for part 3 of NEMA.